Hi, everybody. This is Mr. Foley, and welcome to 6.2 stoichiometry, reactants to products in reverse, so products to reactants. Little heat calculations. How warm will it get if I burn this? And molarity stoich, which means reactant to product using molarities, product to reactants using molarities. So stoichiometry is the mathematics of chemical equations. So that means we're going to change from one thing to another. Crazy, but it's true. How much product can I make? Given something. How much reactant is needed? Given something. How much leftover material will I have? Given something. How effective is this reaction? Which is percent. Again, given something. So this is the whole shebang, and this is where the bread is buttered and the money is made in chemical engineering and all that other stuff. Design a process to make a certain amount and do all these other great things. So chemical quantities can be converted from one type of substance to another. I'm going to turn nitrogen into NH3. We know this. We've seen these reactions, right? Coefficients represent particles, which will be moles, okay? So remember how we said a little bit before, we're going to go through moles all the time. Always go through moles, always go through moles. So looking right here, I'm going to emphasize the one. 1 mole of nitrogen needs 3 moles of hydrogen. Hey, whoa, weird line. And 1 mole of nitrogen makes 2 moles of NH3. So you can see that relationship is based on the coefficient, right? So those coefficients tell us everything we have. If I have 5 moles of N2, so 5 moles of N2, I would need 3 times as many, 15 moles of H2, and I would need 2 times as many, 10 moles, well, not need, but I would get 2 moles of NH3. Now, it's pretty easy when it's pretty easy, but what happens when we actually have weirder numbers, okay? So we're going to show how we can cancel units and make all that happen. So remember, whenever I do this, the last podcast we did, we canceled whatever unit we wanted. So canceling units means the given unit is canceled by putting that unit on the bottom, okay? So I'm looking at this part right here, but I'm going to bring it up here, okay? So if I have 5 moles of N2 and I want to do NH3, what I would do is I would get rid of moles of N2, but I would need an equivalency. So do you see how if I had 1 mole of N2, that would equal 2 moles of NH3? I'm going to erase this stuff so it doesn't get too in the way. This is going to be 2 moles of NH3 from my coefficients equals 1 mole of N2. And that's how I would get 10 moles of NH3. So nice, quick, and simple. Now, of course, we're not going to start with moles very often, but we're going to go through moles every time. Converting from substance A to substance B will always go through moles. So you're going to write your given, cancel your given unit, and go into what you want, typically moles of what you want. Cancel the top unit and go into the unit you want. Or go to moles, do moles ratio, go to the unit you want. So we're going to go to moles, do the mole ratio, go to the unit you want. Okay? So here we go. I have 25 grams of S. How many grams of SO3 forms? Write your given, go to moles. Do you see how this is going into moles? I'm canceling grams of sulfur. 32.06 grams of sulfur, by the way, that came from the periodic table. And that equals 1 mole of sulfur, right? So it's equal each other. So I'm multiplying by 1. I'm not really changing the amount, but I'm changing the unit here. So grams of sulfur, goodbye. Grams of sulfur, goodbye. So go to moles. Mole ratio, right? So I want SO3. So I want to get out of moles of S. So I put moles of S on the bottom. And we go into moles of SO3. I need an equivalency. 2 moles of SO3 equal 2 moles of S. Now I'm in moles of SO3, but I want grams of SO3. Cancel my moles of SO3 and go into grams. Little g stands for grams, and little g stands for go to the periodic table. And that's what you do. Note, whenever you have moles over moles, use coefficients. Little g means go to the periodic table. And when you're doing the math, you multiply things on the top and divide by anything on the bottom. So how many moles are required to produce 350 grams of SO3? I've got my balanced equation up here. I have 350 grams. of SO3. You're going to see me do this all the time. I want moles of O2, and I'm going to write it and circle it a whole bunch so I don't forget where I'm going. So I'm going to start with I hate you grams of SO3, and I want to go into moles of O2. But before I go into moles of O2, I have to go through moles of SO3. So little g stands for grams, and little g stands for go to the periodic table. So that is 80.06. 1 sulfur plus 3 oxygens equals 1 mole. That's a 6. Now I'm in moles of SO3, but I want to go into moles of O2. Moles of SO3. I hate you, moles of SO3. Going into moles of O2. Moles over moles use coefficients. 3 for O2, 2 for SO3. That's the unit I want. All my units have canceled except for the one that I want. And I get out my calculator. 350 divided by 80.06 times 3 divided by 2 is 6.56 moles of O2. How many molecules of O2 are required to produce 100 grams of SO3? I'm sorry, that's a capital G. It should be a lowercase g. So my given, 100 grams of SO3, hate you grams of SO3. I'm going to go through moles. Always go through moles. Always go through moles. Where are you going? I'm going through moles. See you there. I'm going there too. And again, the little g stands for grams, which means go to the periodic table. And 1 mole equals the go to the periodic table number. That's literally what molar mass means. Molar mass of uno molar. But I don't want moles. I forgot what I'm looking for. Molecules of O2. Molecules of O2. Okay. So I'm in moles of SO3, and I want molecules of O2, so I'm not there yet. So I can go out of moles of SO3 and go into moles of what I want. I want molecules of O2, but of course, first I have to go through moles. Moles over moles use coefficients. So coefficient for oxygen is 3, and SO3 is 2. But I don't want moles of O2. I want molecules. So I'm going to cancel moles of O2 by putting on the bottom. I'm going to molecules of O2 on top. Now, 1 mole of O2, remember, is a big, long number, 6.02 E23. And I get out my calculator. Dun, 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 dun. I have 100 divided by 80.06 times 3 divided by 2 times 6.02. Remember, second comma, 23, enter. And a lot of you are going to make this mistake. You're going to say 1.13 and think that's the answer. Look all the way down on your calculator. Your calculator says 1.12704072 E24. So this E24 is actually the most important part. This is like if I told you, you won the lottery, you won 100. Oh, yay, $1 billion. The billion is the most important part. This is the most important part, even though I wrote it in yellow. E24 molecules. Let's keep on keeping on, my friends. 200 milliliters of 0.75 molar CuSO4. How many grams of Fe will I need? Remember, you got to start with moles. So whenever I see molarity, there's my molarity, I write moles equals MV. So the molarity I have is 0.75. The volume I have is 0.2, not 200. 0.75 times 0.2 is 0.15 moles of CuSO4. Okay. So now we do our conversion like we did before. So what we want is grams of Fe. Okay, but I'm going to start with 0.15 moles of CuSO4. I hate you moles of CuSO4. I put it on the bottom. I want to go into moles of Fe. Excuse me. Oops, and I crossed out. No, I don't want to go to moles of Fe. I want to go to grams of Fe, but first I go to moles. So boom, boom. Now I'm in moles of Fe. That's what I'm in. But I want to get out of moles of Fe and go to grams of Fe. But where did this number come from? This number came from the periodic table, right? So now I got to bust out my calculator again. 0.15 times 2 divided by 3 times 55.85 is 5.59 grams of Fe. All right, here we go. I'm going to jump all the way down to the bottom part here. When 9.5 grams of iron react, what molarity? I'm going to have to do moles equals MV. What molarity of FeSO4 will form if the system is in 125 milliliters? Molarity. I will go to moles of FeSO4, so it's grams of Fe. I'm going to go into moles of FeSO4, then use moles equals MV. So I'll start off down here. I don't like putting this in here now that I look at it. Given 9.5 grams of iron. I hate 2 grams of iron, so I put it on the bottom. 1 mole of iron equals 55.85 grams of iron. Got that number from the periodic table. Then I want moles of Fe2SO4, so I'm going to get rid of moles of Fe and go into moles of Fe2SO4. And by the way, this number and this number are the coefficients of the balanced equations. Hey, I remember that. So let's do that. 9.5 divided by 55.85 divided by 2. Remember, multiplying or dividing by 1 is like kissing your sister. It doesn't do anything at all. So that is moles of Fe2SO4 3. Now I got to do moles equals MV. So I knew it was coming, right? Moles equals MV. My question is molarity. What molarity? So my moles are 0.0850 equals molarity times, not 125, but 0.125, make it liters. So I do that in math, take the answer I have divided by 0.125, and I get the molarity of 0.680 molar. All right, heat and stoich. So heat and stoich. This is very important. If you've turned your heat on this winter, and I believe you have, then this is something that works for you. So endothermic and exothermic. Endothermic absorbs heat. It feels cold. The delta H will be positive. This is one of the ways we indicate heat. Kilojoules will be on the left. That's another way we indicate heat. An exothermic reaction, the prefix exo means it's coming out of, and endo means into. So we have an endoskeleton, means we have a skeleton inside of our skin. And if it's exothermic, heat is exiting the system. So it's going to feel hot like fire. Delta H is going to be negative, and kilojoule is going to be on the right because heat is a product. So let's take a look-see. Delta H tells you the heat is absorbed or released for a balanced reaction. So here we go. This delta H is positive 178. So the delta H is positive, so the heat term is going to go on the left. Heat is required, the reactants gain heat. 178 is the coefficient that we'd use for calculation. So see this right here? Now 178 kilojoules is just like 1 mole of CaCO3. Okay? Now, I just want to emphasize that this is a balanced equation with 1s as the coefficients. If the delta H given was negative 99, that means that heat is going to be a product. Delta H is negative. So the heat goes on the right. Negative 99 is the coefficient that we'll use for calculations. So notice here, this goes with the balanced equation. 1, 1, 2, 99. All right, let's do some math. How many kilojoules of heat energy is involved in the reaction if 3 moles of calcium carbonate were to decompose? So my given number is 3 moles of calcium carbonate. Just like before, I hate you, calcium carbonate. My coefficient is 1. I want to figure out how much heat it is. So up here, remember how positive 178 means that I would put 178 kilojoules on the left. Put a plus right there. And that's it. So let's put it in the calculator. 3 times 178 is 534 kilojoules. That's some kind of heat being released. Okay. Now let's take a looky at hydrogen plus chlorine makes it 2HCl. So there's a balanced equation. and it says plus 185 kilojoules. So just treat that just like a regular coefficient. How many kilojoules of heat energy is released if 5.05 grams of hydrogen gas reacts with excess chlorine? Whenever it says excess, you don't worry about it. So if I told you I have excess Ticonderoga pencils, that means I don't need any more. I have all that I need. Okay, so you can always just ignore it when it says excess of chlorine. So I have 5.05 grams of hydrogen. I hate you, grams of hydrogen. I'm going to put that on the bottom. I'm going to go through moles of hydrogen. Okay, moles of hydrogen. And I use 1 mole. This number comes from the periodic table. Moles and grams, 1 mole equals, go to the periodic table of grams. Now that I'm in moles of hydrogen, I'm going to cancel out moles of hydrogen. Remember, I need an equivalency here, right? 1 mole of H2 will give me 185 kilojoules. So then all I have to do is bust out my calculator. 5.05 divided by 2.02 times 185, and I get 463 kilojoules. All right. Oof. This doesn't end, does it? Let's see. I think, we'll do a molecule one, I guess. No, we'll do 2 more. So how many molecules of HCl will be produced at 2.5 moles? So let's go ahead and go through this. 2.5 moles of HCl. And I'm looking for molecules of HCl. Oh, this is just a review one. I tried to trick you. Moles of HCl, and I'm looking for molecules of HCl. So I go from moles of HCl, and I'm going to go into molecules of HCl, keeping you on your toes. 1 mole is, remember, there's 6.02 E23. Whenever we're dealing with molecules or atoms, that's the number we use when it compares to moles. 2.5 times 6.02 E23, and I get 1.51 E24 molecules. I like MC for molecule abbreviations. HCl. What? Oh man, I wrote down the wrong thing. 2.5 moles of hydrogen. I'm wrong. I'm going to erase that real quick. 2.5 moles of not HCl, but H2 times moles of H2, moles of HCl. Notice I have to go into HCl first. It helps if you read your question. And where's my coefficients? So 2 HCl and 2 moles of H2 times, now I'm going to do 1 mole of HCl and 6.02 E23. And looky, see how these cancel out? This is going to be molecules, HCl. See how 2 and 2 cancels out? And I get the same answer anyway, 1.51 E24, but I got lucky. Molecules of HCl. All right. How many kilojoules of energy is needed? Is absorbed if 1,950 grams of KClO3 were to decompose. I should break down the number instead of just the substance. Come on. Okay, so 1,950 grams of KClO3 times grams of KClO3 and 1 mole of KClO3. So I got to figure out the go to the periodic table number for potassium. So 39.10 is potassium. Chlorine is 35.45 plus 3 times 16. So 3 times 16, enter, plus 35.45 plus 39.10 is 122.55. And then this gets me into moles of KClO3. So I want out of moles of KClO3, and I want kilojoules. So I can go from moles into kilojoules, and I believe I will. 156 kilojoules. And KClO3 is a coefficient of dose. So let's see what we got. 1950 divided by 122.55 times 156 divided by dose is 1241. Oh man, I got 1241. My little answer key thing down here. says 12:48, but you know what? I'll take that. That's good enough. All right, you know what? These are all the same, and we hit 20 minutes. That's good enough for me. So I'll just say toodles.